Hello everyone, friends. We are currently on the campus of Bauman Moscow State Technical University, and today we're visiting the Engineering Center for Stratospheric Systems, where Arkady Didkovsky will give us a tour and tell us about what they do there. Let's go.
We have several base locations, and this is one of them. Testing is conducted here. In the envelopes, we have experimental production, cutting, welding, and onboard equipment. The design bureau is also conveniently located here. At our rather extensive sites, we diligently work with various metal products, including precise welding, efficient cutting, careful bending, and so on. And we also have a dedicated testing ground. Let's go. This is precisely where the welding is directly done. We recently received some film more than 2 meters wide, a 5-layer film. Most of the welding operations take place here. At the moment, we have several types of welding machines. This is a thermal impulse welding machine. Sergey, could you please show us a seam? So the operating principle of this machine is that a nichrome strip heats up in just a few short seconds due to a high electrical current. Then the cooling process subsequently takes place, and that's how the seam is effectively formed. All the important mode parameters are critical here: the mode speed, the heating speed, the cooling speed, and the maximum temperature. All of these can be precisely adjusted on this particular machine down to the exact hundredths of a second. The operational mode is conveniently set here. There's also the valuable option to easily change the electrode, so you can readily install a longer 1 meter electrode, for example, instead of a standard 30 centimeter one. Right now, electrodes with a considerable width of 30 millimeters are currently being manufactured. So this is a 1 meter electrode.
So this is a replaceable part?
Yes. This particular part of the table can be easily removed. And you can also conveniently install specially shaped electrodes right here. We work with several distinct types of films, including both polyethylene films and polyurethane films. This is a durable polyethylene film, carefully constructed with several distinct layers, including a crucial barrier layer. And now, Sergey, our chief technologist, will expertly demonstrate precisely how it effectively functions. The pressing is now complete. After the sound signal finally ends, the heating automatically stops, and then immediately comes the cooling phaser, resulting in a very neat little seam like this one. So these are like the sealers you see in Okan, only, well, they can only envy this one. It's a bit of a different quality. Here you can clearly see this particular seam. This is the so-called overlap seam, which is especially strong and robust because the entire load is effectively distributed across the substantial area of the seam. And accordingly, therefore, the kind of load that usually occurs on casings such as this is absorbed most fully by the material, thereby reducing the risk of defects and failures.
So if the material is larger, you move step by step?
Yes, step by step. One seam overlaps the other. There are also various tricks when working with materials, depending on their properties during welding. Our colleagues know all of this, are skilled at it, and have generally already adapted. The remarkable machine was entirely invented, meticulously designed, and expertly manufactured right here by our dedicated employees, our exceptional team. And in general, there are plans to create a second such machine in the near future, an even more advanced one, but a lot has already been done and perfected on this one as well. This is the second machine we are observing. This particular machine is no longer operating with a thermal impulse mechanism. Instead, it is also entirely thermal. Here, within this system, you can clearly see several distinct operational zones. This is a Chinese store-bought machine that has been modified. It's a fairly inexpensive option. Here there is a heating zone, a cooling zone, and a sealing zone. So here, several precisely positioned rollers provide sequential pressing, then meticulous perforation, and the seam is formed directly and efficiently. In this case, the seam is a bolt seam, not an overlap seam. You can see what it looks like here. So this is a piece of the shell for 2,000 cubic meters. This is what the seam looks like. It doesn't bear the load across the entire area of the seam, but only along the line where the load is applied. The seam is not designed to withstand heavy loads. It is intended simply to hold the gas in place. And as you can see, here is a shell with a volume of 2,000 cubic meters. It's quite compact, folded in a zigzag checkerboard pattern. Right now, it's in 4 pieces. 2 pieces are on the truck and 2 are in storage. The guys are already welding the final seams.
Do you purchase different types of film, and do you test or check them in any way?
All the fumes undergo testing. They are tested for tensile strength and for gas permeability.
Is all of this entirely done here as well?
Not exactly. We don't test for gas permeability here. Our colleagues handle that. Here we test for tensile strength. Moreover, we have a biaxial fabric loading machine that allows us to simulate pressure loading, because when the envelope is filled under the pressure of a balloon or airship, the fabric experiences biaxial loading. And so with one of our advanced and highly capable machines, we meticulously simulate this specific and complex type of loading condition. Here's a neat little seam, very soft. This is a 50 micron film. At the seam and material boundary, no defects form even under significant loads. That is, all of this is important to us, not just in terms of strength, but also in terms of gas permeability. Here we can clearly see that such significant defects do not form. You can weld complex large products with these precise seams step by step and accordingly achieve perfectly airtight joints. Materials are tested not only under normal conditions, but also at sub-zero temperatures, that is at minus 65 degrees. Measurements are taken both for helium permeability and for strength. It is quite clear that materials behave very differently under these conditions. For example, with polyethylenes, we see that the elongation percentage drops from 400% to 10 to 20%, meaning they become brittle at low temperatures. Well, this is to be expected. All of this is important. It's crucial to monitor before manufacturing the shells. There's a control unit for it, which also supplies power. Here is this roller. It's currently in the final stages of development. It already welds, and our colleagues have made several products with it, but they discovered a number of shortcomings during operation. For example, the edge of this roller is exceptionally sharp and unrefined. When the seam is pressed with this particular roller, its overly keen edge causes a noticeable and undesirable thinning of the material. This thinning acts as a stress concentrator, but otherwise the roller is quite convenient. Here, for example, there are sliding contacts connected to the temperature sensor and the heater. The roller is coated with a Teflon layer, so you don't need any adhesives or anti-adhesives to prevent the roller from sticking to polyethylene or polyurethane welds on its own. It's just like a frying pan. You lay the product out on the table, do some minor repairs, or for example, if you need to make a shaped seam, this kind of roller allows you to do all of that. Rollers of this particular type haven't been developed in Russia for, I genuinely think, at least a good 30 to 40 years. This right here is our advanced onboard computer system. Just this past Tuesday, it successfully underwent its flight tests and passed them with great success. Throughout the entire flight, right up to 100 meters above the ground during landing, we maintained continuous communication with it via radio channel every 10 seconds. It transmitted the full telemetry package, remotely collected data from a sensor located outside, and measured the temperature and pressure inside the body itself. Here is the body with solar panels for the onboard computer. Moreover, it was such a sunny day that while it was minus 60 degrees outside, it was plus 43 degrees inside, switch overheating. We thought we would need to heat it, but it turned out we actually had to find a way to get rid of that heat outside. And what's most interesting is that even under strong electronic warfare conditions and heavy radio interference, we were able to get a stable GPS track up to an altitude of 8.5 kilometers. So that's commendable. I think that with some adjustments, we can increase this altitude even further. So we will continue working on preserving the coordinates of the device itself so that we know not only its altitude by barometer, but also its exact location. Right now, in areas where there is electronic warfare, this presents certain difficulties. But overall, this method of rewinding the shell significantly reduces the labor intensity of the process and improves the quality of the work. Because everything happens in one place and people don't have to run around anywhere. So the shell itself is 30 meters long, And for it, you would need a 30-meter long table, and all around it, there would be weights, counterweights, guides, and everything else, right? But here, everything is done in just 6 or 8 square meters. In this room, you could make 2 or 3 such shells at the same time.
And to work on it, 3 people are enough, or could even 2 people manage?
Even 2 people could manage.
Even 2 people could easily manage this particular task. Basement level 1.
Come in. So this is a 40 cubic meter gas shell. It's been undergoing extensive testing for 2 weeks now. Basically, it's being tested for its gas permeability. So we have comprehensive data on the gas permeability of the fume itself, and also on the gas permeability of the seams. But in addition to that, the shell has various other elements up top. There's an appendix installed on the side, there's a filling hose, and so on and so forth. They are meticulously made from various different materials and carefully welded together in distinct and specific ways. So it is critically important to thoroughly test the entire shell as a complete and integrated product. Extensive and rigorous tests were then conducted, first with the gas hose positioned on top, then it was carefully removed and securely retied, and subsequently tested again, and finally it was then gradually lowered. Now we're at the testing stage where the top is pulled down to the bottom, and the gas hose itself, which can also be a source of additional helium leakage, is at the bottom, meaning the gas doesn't actually touch it. And right now, nothing is changing there. They just regularly take readings and plot a graph. Well, the buoyancy here is minor, so we're not really worried about it flying away. We see 6.8, 6.87. We usually run the tests for at least a couple of weeks. In principle, a week would be enough, but we prefer to play it safe. So the previous tests we conducted were for gas permeability. This red part here is the filling hose, just so we don't lose track of it. They lasted for a month, and they were inside the hangar. We found that even though the hangar is supposed to block out the sun from all sides, the buoyancy still changed a lot depending on the time of day, be as much as 2 kilograms. That's why we moved further away from infrared radiation down into the basement. Here there's no direct sunlight at all, and since it's deep underground, the temperature remains quite stable. So we no longer observe those daily fluctuations. We have a stable line in terms of temperature, yes. There's a kind of planetary alignment that is clearly visible in the weight data, in the precise weight measurements here. A sensor is built into the shell from the start, and it's autonomous. It's powered by a small battery, just a little ball. Inside there's a temperature sensor, a pressure sensor, a voltage sensor, and it transmits readings to the receiving station in real time. Here we can clearly see that it's currently displaying 102.08 kilopascals. The ping is accurately tracked. Here is metric shows precisely how many seconds ago the last message was successfully received. A new message comes in every 5 seconds. It clearly shows here that there's an SD card, so you can easily enable continuous recording. And the precise temperature is displayed as 19 degrees Celsius, so any significant temperature deviations are also meticulously recorded here. You can connect several different sensors, up to 4 at the very same time. An SD card is already inserted here, so you can conveniently use it to build comprehensive graphs. For example, most of the differential manometers we've extensively worked with. Well, first of all, there are a bunch of useful adapters from the tube to the pressure receiver. Secondly, some of these differential manometers leak by themselves, so we can't tell what's leaking, the manometer or the casing. But when the sensor is inside and everything is received via radio channel, it's very easy to rule this out, especially since continuous recording has proven itself to be very reliable. Several of these control panels have already been made. There are also 5 of these sensors, and exactly the same sensors are installed inside the envelopes for flight in order to monitor overheating and internal pressure.
And once again, what exactly is the primary and most important task of this particular sphere here?
Well, right now it's undergoing testing, and we're constantly refining the technology. These spheres have already flown, but they're heavy and expensive, so we're trying to make them lighter and cheaper. This particular sphere is twice as light as our previous version. Right now, it's already on its 3rd day of testing, and the pressure graph is stable. It's airtight with regular air. With regular air, the pressure inside is about 3 kilopascals if we zero everything out.
How many cubic meters is that?
It's about 20 cubic meters. So it's a sphere with a diameter of just over 3 meters, about 3.5 meters. And its purpose is to keep us at altitude so we don't rise up. If you just release such an envelope into the atmosphere, it will rise, expand to its full volume, and then either burst or release its gas and fall down. And this will happen in no more than 24 hours. And in this case, it will stabilize at a certain altitude thanks to this envelope, because it gains weight as it rises due to aerostatics.
All right, I understand.
It's simply the fundamental law of aerostatics. It consequently gains this weight. You can clearly see here, for example, that one of the pulleys tore this happened during a test at 10 kilopascals. And these catenary belts, the intricate rosettes there, the way all these rosettes are intricately connected and so on, the crucial load transfer, all of this comes with a lot of significant nuances and subtle complexities.
In practice, we really had to deal with this and look for effective solutions.
Here we have the design bureau testers. They were carefully monitoring yesterday's important flight. Here actually it's mostly the trajectory. There it just updated. Mostly it's the precise trajectory of the vehicle from Moscow. We were flying to the left of the rather significant Chkalovskoye reservoir. This is indeed the precise starting point, and this is the exact landing point. The satellite barely picked up anything of significant information. Now, I will proceed to show you the actual trajectory via the dedicated radio channel. This is our current altitude reading. So this is the barometric altitude and this is the GPS altitude. You can clearly see that from a certain altitude, they started jamming us. That's at about 8 kilometers, a significant height. So these spikes here, that's standard operation of electronic warfare. It's trying to say like, guys, you're falling, pull up the nose. And after that, the drone goes into a stall. Here, according to the barometer, the transmission was quite stable. This is the track that our onboard GPS sent us via radio channel. And after that, the electronic warfare started interfering, spinning it around, and so on. So at that point, we no longer knew for sure where we were. But the accuracy of the prediction there was literally, I think, about half a kilometer. This is a biaxial loading machine. Basically, the guys typically use it to thoroughly test various types of tapes as well.
So here already, right, it will work?
Yes, here it can be done. This particular machine was also meticulously made here. Here, a piece of fabric or a film material is securely fixed into this specialized fixture, and then it is precisely torn either in a single direction or in two distinct directions. A durable tape can also be carefully placed within it. So that's precisely how this intricate process works.
You can choose one of two directions or both at once, right?
Yes, you can do both directions at once. So it's just a more complex and intricate shape of the sample itself. Here is one particular sample. It was intentionally torn, and the maximum load it could withstand was carefully measured.
What kind of mass, if you can put it that way, can this instrument accurately measure?
It's not much here. This is about 5 centimeters. In general, the strongest fabrics we use usually have a tear strength of several thousand newtons. So this machine is capable of handling such loads.
What exactly are your upcoming plans in this particular line of work?
Well, you can take a detailed look at the comprehensive flight plan. We extensively discussed the specific plans for a significantly long-duration flight at the very end of June with Rosaviacja. So we considered two launch sites, one in Vandech and the other in Kirchach. This is already a route lasting over 50 hours. Here you can see several regions, Leningrad, Ivanovo, Vladimir regions, they are all affected. Here we would have to cancel 8 flights to ensure that our flight does not pose a risk to air traffic. Here, near the Gorky Reservoir, we found a spot where, in principle, there are no flight restrictions. There are several air routes that border this area near the reservoir, and if accordingly, the takeoff is in the direction of the north or northeast, then we do not cross these routes. Here, instead of a circular sector, we simply create a sector in the shape of a triangle or quadrilateral. Well, the route for 50 hours is not much different from one another. That is, as you can see here, there is only one point, yes, the takeoff point. That is, their shape is the same, it's just that one route is shifted a little relative to the other. So at the beginning of next week, we will update this forecast and we'll already be discussing specific restrictions. For example, right now over Russia, the atmospheric current is quite weak. These are observed speeds of approximately 17 kilometers per hour, then 9 kilometers per hour, and so on, indicating a very gentle flow. This is for an altitude of about 18 kilometers. If we go a bit higher, here we already have a steady eastward flow, just from east to west at a speed of 30 kilometers per hour or even 50 kilometers per hour. And if, for example, we were to switch to the winter period, then we would observe a different pattern. For instance, let's look at January of this year. Then at these altitudes, we see a stable vortex that exists throughout the entire thickness of the atmosphere with very high speeds, 250 kilometers per hour, 150 kilometers per hour. And for almost the entire winter, it remains stable, though sometimes about once every few years, there is an event when it splits into two such vortices and they then move independently of each other. But after about a week, this fascinating phenomenon collapses back into a single stable vortex, and you can then travel along it much like a satellite. This allows for constantly passing over the same specific regions, and if there are many such devices, then we can achieve continuous communication within the entire region or monitor it constantly and effectively. So it's quite interesting and highly beneficial.
It's interesting and cool because you don't need to launch a satellite with an expensive rocket. Well, my friends, I think that's truly all for now. I'd really like to thank Arkady for giving us this truly fascinating and insightful tour. It was very interesting to see precisely how everything works here. It's great to see that everything is at such a remarkably high level. I'm glad you found a place where you can develop in a direction that genuinely interests you and will be useful for a greater common cause. Thank you again very much indeed.
Thank you.
See you again.
See you.
Great. Thank you.